So context learning and data simplification. I've somehow put these things together under the heading of computing summaries in mobile phone. We'll see as we go along. So yeah. Right. So the idea is this, that mobile phones have sensors. They can sense location. They can sense light, sound, accelerometer. There's camera. They have actually lots of sensors. And this is, in fact, screenshots from my mobile phone itself, that you can see that it can sense the sound, how many decibels it is, the light. This is the magnetic field sensor. And this is accelerometer, where the plots are not very visible, but you get the idea. It senses how much acceleration you have along each axis, x, y, and z. Okay? So the good thing, along with the fact that mobile phones have sensors, is that most people have mobile phones. So that is an opportunity to sense signals everywhere. This is kind of the ultimate sensor network you can imagine. There are sensors everywhere, where you want them, where you don't want them, and anywhere you can think of. Okay? So that is a great way to learn about what is going on in different places, what people are doing, and all that stuff. So where can you use? You can upload all these sensor data for offline analytics. You can use inference or learning on that data for better adaptive services. As you learn what people like, what they do, you can adapt your services to that. The challenges are that there is a lot of data. Okay? And as your phone records data from all the sensors continuously, let's say one data point every second or every millisecond, all that data, if you are going to upload it for data analytics, is going to be costly to store, costly to transmit, and costly to analyze later on. There's the problem of privacy, that when you upload it, data is out of your hand, and people don't like giving out their data. And the other thing is that sometimes you need to take immediate action. We'll come to examples of that in a minute. But if, let's say, you are trying to adjust the profile of your phone, depending on how much light it is, you want to adjust the screen brightness, or you want to increase the ringer volume if there's a lot of noise, that has to be done immediately. You can't upload it, analyze, come back, and do all that. So for all these things, there are reasons that we want to do online computation on the phone itself. Okay? So that computation has to be very fast, very lightweight, because the phone is not a big server. So the part one of this talk is learning and adapting to the environment, what we call the context of the phone, where it is being used. In particular, we'll look at detecting if a phone is indoors or outdoors. Part two is simplifying data. So when you collect all this data, a lot of it is redundant. Nothing much is changing. The phone is just recording sensor values, and all successive values are more or less the same. We'll show a method to filter out all this redundant data and keep only the important data points, and do that in real time. Okay? So let's do it. The first thing is detecting indoors versus outdoors. So all the sensors on the phone, you can imagine, are somehow or the other affected by whether you are indoors or outdoors most of the time. So light, for example, you can check that sunlight is very bright. In fact, if I do a measurement here, the light will turn out to be something like a few lux, below 100 lux probably, whereas if you just do it outdoors now, it will be over 1,000 lux. So light is a very good indicator. Cell signal strength, we found, is also a good indicator. As you move indoors, there's attenuation from the walls and such, so cell signal falls. The magnetic field strength varies a lot more indoors, because indoors you have appliances, cameras, computers, whatever, and they cause the magnetic field strength to fluctuate much more than outdoors. Sound outdoors is typically noisy, particularly in cities. All these other things you can imagine somehow or the other are affected differently depending on whether you are indoor or outdoor. Okay? And there's GPS. If you can't get a location fix, it is likely that you are indoors, so the ceiling is blocking signals. Okay? So let's see. People have tried to use GPS, and the idea is that if your localization accuracy using GPS drops a lot, it is likely that you're not getting satellite signals very well, therefore it is likely that you're indoors. So we tried that out, and it turns out it's not as accurate as we thought it would be. We thought that indoors it's obvious, there's no satellite signal, it will be, GPS is the ultimate detection mechanism. But that's not quite the case. It turns out it gives 70 to 80% accuracy, but not much more. And GPS is very energy hungry. It's probably the most energy hungry thing on your phone. So we tried out different sensors. GPS consumes things at the rate of about 400 milliwatts. Wi-Fi is the next highest thing, which consumes at a 200, 250 range, and everything else is actually much smaller. So what we would like is to use these smaller, lightweight sensors and get much more accurate results than what we get with GPS. Okay? So someone has already tried that. This paper is from Census 2012, and it's a very nice piece of work. What they do is they take 3 different sensors, light, cell, and magnetic sensor. In the light, they put a particular threshold and check to see if it says indoors or outdoors. In the cell signal, it tries to see when cell signal drops very fast or rises very fast, which signifies that you're moving indoors or moving outdoors. And in magnetic variance, it sees how fast the magnetic field is changing. Okay? It takes these 3 detections and adds these results, takes their confidence into account, and outputs a final result. Okay? So that is a very nice method, and we tried that out. So in the paper, they get something like 82% accuracy, and we got something in the range of 45–50% accuracy, okay? Which was kind of surprising. So why does that happen? It happens because of this. So let's say you take light intensity, okay? Light intensity varies by place. This work was done in US in places where the sunlight is very bright. But we were doing our experiment in Edinburgh in the winter on a cloudy day. Okay? So where they had a threshold of 2,000 lux to detect that you were outdoors, in our case, the light did not go much above 1,500 in the daytime. Okay? So you end up getting the wrong detection all the time. So in all these pictures, the shaded part is indoors, this part is outdoors. This is their threshold, but it always stays below it. The ideal threshold would have been something around here. Okay? The problem is that they had set this threshold, but they didn't know how it would be in other places. The same problem occurs in all other types of signals. So magnetic variance, in this case, does not produce the right result. So this is the threshold, and only 2 cases it goes above, like this, but it stays below where it should be above in the indoor case. Cell signal does not fall as fast as you would like when you're moving indoors or outdoors, but as you move from room to room indoors, cell signal can actually jump quite a bit. Okay? All this ends up confusing the detector, which gives wrong results. Which means whatever algorithm we design has to be adaptive. It has to learn from experience. Okay. So we made an app that collects data from all sensors. Okay. The idea was that instead of using just those 3, if we use all the other sensors, maybe we can get something better. And we had an interface so that when the user moves from indoors to outdoors or vice versa, they can enter that fact that I have moved indoors or moved outdoors. So this is going to appear at Census 2014, okay? Which is a great conference. You can check with Hamid. So we tried the following idea, that since we need an adaptive method, why not try a machine learning trick? So we tried learning the thresholds and using all the sensors. We used supervised learning, which means that from our collected data set, we give the system some data labeled indoors and outdoors properly. it learns from that, the characteristics, the patterns of indoor and outdoor signals, and then tries it on unlabeled part of the data. Okay? When we did that, we got very good results, like 87, 98, and above 90%, which is awesome. But you remember the problem with IO detector was that they had also done something similar, just that they had found the thresholds manually, and their result did not work in our environment. So we thought, what happens if you learn this in one environment? This we did inside our campus, and try it somewhere else, like in the city center. So when we do that, we found that the performance drops a lot. So the red bars show the new results. So we did training on the university campus. The testing was done in city center and residential areas. And now the performance is much lower, 60, 70% kind of. Okay? So we still have not solved this problem really, that you are learning in one environment and being tested in a different environment. So what can we do? We need an algorithm that actually learns during use, because you cannot possibly go to all possible environments and get all that data. Therefore, it has to learn as it sees new environments and new data. Okay? And the difficulty of that is that it needs indoor-outdoor estimate. How is it going to learn if you don't provide it labeled data? If someone doesn't tell it that this is indoors or outdoors, there's no obvious way it can learn. So this is the second idea. Use the output of the classifier itself for training. So the classifier gets constructed using labeled data. Here is the classifier. It now sees new data coming in. It outputs an indoor-outdoor. You can use that to rebuild your classifier. Use that as a feedback to your classifier construction, and you update your classifier to take into account this thing. So you are using the output itself as the label. Okay? Very good. That looked like a promising approach. We tried that. Here I'm showing only two learning methods, like naive Bayes and decision trees. What happened was that in the pure supervised case, we had these results. With self-training, by the way, this method is called self-training. With self-training, we are getting slightly better, but not a lot better. Okay? We are getting something in the 75-80 range. Okay. Which is OK, but not that great. Because you see, 50% is very easy to get. 50% is kind of your baseline. You don't need any training, any learning. I can just take a coin, toss it for heads and tails, and that prediction will have 50% accuracy. Okay? So getting 60 to 70 is not that great. We can say it's good only if we get 90 or close to 90. Okay? So we need to do better than this. And for that, we need to figure out what is the problem with self-training. So we see it doesn't work as well. The possibilities are that the classifier output has too many errors. So the output is not perfect, which is why we are doing the self-training. Maybe the fact that the output is not perfect is causing it to learn incorrectly so that it doesn't do so well. The other possibility is that the nature of classifier output is not suitable for its own retraining. We don't know which of these is true. Okay? So we tried something else, that we will give it some noisy labels and see what happens. How this helps in the previous problem, I'll come to in a minute. So this is what we did. We gave it new labels with 50%, 60%, up to 100% accuracy. So each new label we supply to it, we toss a coin, and we give the correct label with this percentage of accuracy. In other cases, we give it the wrong label. Okay? So the observation is that if you have about even just 60% accurate labels, it still gives pretty good results, like 80% or above. Okay? Whereas, so with 60% accurate label, the classifier does well, like 80% or something. But the classifier output itself, you'll remember, had about 60% accuracy. And it still did not manage to learn well from that data, right? That means that it's not just a matter of incorrect labels. It is not just that the labels are incorrect that is causing it not to learn. It is that it is incorrect in some systematic way, which is causing the classifier to get confused. Okay? So this is the final idea, that because the classifier's output itself does not have enough information for it to learn, we are going to use two classifiers. Okay? The idea is that the output of this classifier will train this classifier, and the output of this classifier will help to train this classifier. These two classifiers probably will have different characteristics. They will have different types of errors. So that the errors, so in this case, likely the error of the classifier itself was getting reinforced as it learned from its own output. If the two classifiers have two different types of errors, one can learn from the outputs of the other. So if you have one classifier that is good in the city environment, it can help the other classifier to learn the city environment, whereas if one is good in the campus environment, it can help the other to learn that. So we built two different classifiers. One has these sensors. One uses these sensors, light, time, cell, and proximity, and the other uses temperature, sound, magnet. Okay? So it works this way, that we use label data to build classifier 1. We use label data to build classifier 2. When unlabeled data comes in, both of them output a result. We take the result with higher confidence and feed that back to both the classifiers to update them. Okay? So this method is called co-training. That is, there are two classifiers. Each helps the other to learn. And with that, we actually get very good results. We get, if you use both classifiers as naive Bayes, we get like 92% or something. If you use one decision tree and one naive Bayes, we get close to 90, and both decision tree just below 90. Okay? So that is the method we figured out works. Okay? This is, of course, not the end of the story, because there are many other things possibly to be done on this. There are other environments to be tested, other types of context to be learned. But for now, this seems to work reasonably well. And we also tried some things like how fast does it learn. So this is the learning curve. As you give it more and more unlabeled data, it can stay static for a while. And then at certain times, it learns really fast when it finds new types of data and some new thresholds are crossed. Okay? Another interesting observation is that if you keep the number of unlabeled instances fixed and see how many of the initial labeled data you need for it to do well, it turns out that up to a certain threshold, it doesn't do well. But once you have a reasonable number of labeled data to start with, after that, it really jumps. And after that, you don't need a lot of labeled data, which means that the initial training can be done with a very small data set. Very good. And the nice thing is that this can be implemented incrementally. It's kind of lucky that naive Bayes is the thing that does well, because naive Bayes is one of those things for which you have incremental construction. Okay? So naive Bayes is just Bayesian inference, right? You need to store counts of events of what is happening. Then you just compute probabilities based on those counts. Okay? And all this is very efficient. Each decision is efficient. The incremental learning of the classifier is efficient because you just need to update counts. And therefore, this is good for real-time learning and use on a phone. So we actually tried out how good it is actually on a phone. Turns out that per detection of indoor or outdoor state, it consumes about 738 millijoules. Whereas in that place, if you use GPS, it is over 4,500. Okay? If you use IO detector, that is slightly harder to compare. The reason is that our method can be measured for one use. Our detector cannot be measured for one use because our detector needs to run continuously. Remember that our detector tries to detect the slope of the cell signal to see whether you are indoor or outdoor. Okay? And therefore, it needs to maintain an indoor-outdoor state continuously. Okay? As a result, our detector needs to run continuously. Otherwise, the slope of the cell signal doesn't make sense to it. In contrast, our method can sleep when not in use, and because it uses only the instantaneous sensor values. Okay, so we tried things out for a 30-minute interval of use based on those values. And how much energy these things consume in 30 minutes depends on how frequently you are sampling in our method and GPS, let's say. So for our detector, it is fixed because our detector just runs continuously. Sampling interval means very little to it. It produces something like that. GPS produces much higher, but if you are using like 4, 5, 6 samples per minute, then GPS is reasonably good. And the co-training based method does pretty well throughout. Okay, so in summary, we have a learning classifier which adapts to new environments. The classifier can be built incrementally, and it can learn from small number of samples. We did some preliminary test as to what happens if you use this to turn on and off your Wi-Fi scanning. Okay? So the problem is that your cell phone is always looking for a wireless access point that it knows. Okay? So when you are outdoors and there's no wireless access point that you know nearby, it is still scanning every few seconds, something like every 15 seconds or something, I think. But when you know you are outdoors and you are not going to connect to a Wi-Fi, it's good to turn off Wi-Fi scanning, right? So if you can detect that automatically and turn off Wi-Fi scanning, you can save over 70% of that energy that it would have consumed. Okay? So also this method works as lightweight on-demand service, and we need to get better ideas of learning rates. We need better theoretical understanding and apply to other learning and adaptation problems. So some of these works are going to be done hopefully soon. So that is about that problem. So now part 2. Okay? Part 2 is simplifying data in real time. So the problem is this, that you have location data. Let's say one person moved like this. Most of the data can be redundant. So maybe this person was standing here for a long time. Okay? We don't need to store all those information. Or when a user moves in a straight line, that is not particularly useful. So going from here to here, all this data is mostly not important. If you can preserve this point and this point, that pretty much suffices. So we want to identify the important points that really represent your data, as opposed to all the intermediate points. And we want to remove those redundant points. Okay? That is the problem. In particular, we need to preserve the sharp changes and sudden turns because that is the important data. So here these 90-degree turns are important. Or if you look at this signal of light values, actually this is the same light values from the previous part, then the light value goes like this. It drops when you move indoors. It has small fluctuations and then rises again when you move outdoors. All these small fluctuations are not important. Okay? What you need to preserve is that the value was high initially, then it drops very fast. This fast drop is critical because it signifies your outdoor to indoor movement. And then at this point, it rises very fast again. Okay? So these sharp features are important, but traditional methods that use smoothing, for example, fast Fourier transform-based simplifications are kind of smoothing, that will not let you preserve these sharp features. So if you do a Fourier transform-based simplification of this, it will look something like this, and you will miss the corners. And these sharp turns are also important when you're doing road network inference. So recently there's been a lot of work where you track people's GPS locations, and from that you're trying to figure out where exactly the roads are. And if you're trying to figure out the roads, what you need to really figure out are the intersections, right? And for that, you need the sharp turns. So that exact point is important. Okay. And we need an efficient method that can work on the phone in real time, because that will save communication and storage. You don't have to upload the entire data set before simplifying it. And if you can reduce the amount of data you have on your phone, maybe you can do faster processing online. So you can do some of your processing on the phone itself. Okay. Another point I wanted to say is that, yes, most of the existing methods don't work online that well. Existing methods for simplifying curves are mostly offline. They assume that you have the entire data and then you try to simplify it. We want to simplify things as we get them. So this point is important. We want to decide here and not after you have arrived at the end. Okay. So our approach is to use topological persistence. Okay? Topological persistence has been a hot topic in computational geometry for 10 years now, more than 10 years. So you can look at this original paper by Edinburgh, Lesher, and Zamorodian on topological persistence and simplification. So it works somewhat like this, that suppose we have a function of x. This curve may not be a trajectory for now. Let's just think of it as a simple function. And we are trying to simplify it, meaning we want to identify the important points of this function. So like this is an important point, this is an important point, but these are not important, because if you remove these and just interpolate here, it still gives more or less the same curve. Okay? So the way topological persistence works is this, that it sweeps the values from bottom to top. There's a line that is going like that. Okay? And it maintains connected components. So in this case, when the line is up to here, there's this one connected component. Okay? Connected components are born at the minima, like it was born here at A. Okay? After this, when it arrives at C, another component will be born. Okay? When it arrives at maxima like this, these two components merge. Okay? These two components merge and they become one component. So we can no longer say that there are two components. We have to say that now there's only one component. So we say that one of these components has died. We say in particular that the younger component has died. Okay? And at that point, we can output a bar like this. The endpoint gives the birth of the component. This endpoint gives the death of the component. Okay? And this bar signifies kind of the size of this component. Okay. After you sweep through the entire thing like this, you get a whole set of bars depending on where components were born and where they died. So this one we already saw. There was another component born here which died here. There's this small fluctuation around the maximum which created a component born here which died here. Okay? Only the first component is very large. It was born here and died here. And there's this other component that was reasonably large which was born here and it died here. Okay? So the large bars kind of represent large components and large features, whereas the small bars represent small fluctuations in your signal. You can think of that as noise. Okay? So if we remove these small fluctuations and small noise, then we get a simplification. In particular, this will, for example, tell us that the important points of the function are this, 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 etc. Okay? Very good. So we will remove these short non-persistent features based on some sort of a threshold. We say that if a bar is up to beta in length, then it is not important. If it is longer than beta, then it is important, and we'll keep that component. Okay. So how do you apply this idea to trajectory? Let's say this is a trajectory, and we apply this. We will sweep, we'll find this is a minimum, and these minimum merge at this maximum. Okay? So it will produce this point, and this point. Out of that, the first and the last are kind of trivial, because first and last point of your trajectory are anyway important. And it gives this point, which clearly is not very important to the trajectory, right? If I remove this point, if you go from here to here, this is a very small error. Okay? In this case, the good approximation would have been A, B, C, D, right? So you preserve this point, this, and this, and that would have given us a very nice approximation. But persistence completely misses that. Okay. So we can't just take that and apply persistence on a trajectory. We need some other trick. The observation is that A, B, C, D are important because they have high curvatures, because there's a sharp turn. So we are going to measure that and apply persistence on that function. Okay? So curvature, if you have forgotten, is defined like this, that if you have a smooth curve like that, take the circle that is the best fit at this point, take the radius of that, and the inverse of the radius is your curvature at this point. Okay? This is the smooth definition. The problem is that we have discrete data like this, and we can't go around fitting circles. Fortunately, there is a simple definition of curvature that works for the discrete case, which is that you just take the angle of turn. So if you are going this way, and now you are going here, this is the angle of your turn. You take that. And you take that as the signed angle. So counterclockwise is positive, clockwise is negative. Okay? So we take the curvature function against time and apply persistence. That will kind of give you these sorts of sharp turning points. Okay? So this work is going to appear in SIG Spatial next month. The problem is the persistence algorithm that I just showed you, requiring sweeping the entire thing, is offline. It's centralized, because you need all the data and sort them first to do the sweep. Okay? We need an online method. So I'm going to tell you how to do topological persistence online. Here the assumption is that we know the threshold beta. Okay? If you don't know the threshold beta, at least I don't know a way of doing the general persistence online. But if you know your threshold, then it is possible to do things online. It works like this. There are two observations, that if you take your curve and the points that are preserved by persistence, then every persistent minimum is the lowest minimum between adjacent maxima. So this is a persistent point. This is another persistent maximum. This is another minimum. This is the persistent minimum. Then this has to be the lowest between these two. There can be other minima, like this one and this one, but these are not the lowest. Between these two persistent maxima, there can be only one persistent minimum, and it has to be the lowest one. Okay. Other point is that if you have a persistent minimum here, then on its two sides, you can find 2 points like this that are separated from the minimum by a value of at least beta. Oh, by the way, and here also this difference is at least beta. Here the difference is also at least beta, and between these 2 points, this is the lowest minimum. If that happens, then this minimum must be a persistent minimum. Okay? So this kind of goes in two directions. One is that if this is a persistent minimum, then this property holds. And this says that if the property holds, then this is a persistent minimum. Okay? So that is the second thing. So therefore, we can do this thing, that suppose we are getting the data in a streaming manner. When we get a minimum, we can check that it is the lowest since the last persistent maximum. Okay? And it is then followed by a point that is at least beta higher than itself before it sees another minimum that is lower. So it just says that here somewhere there is a maximum, or here there is a point. After that, we see that this minimum has a distance of at least beta up to here. We kind of keep a pointer here, and then we follow the trajectory. Here there's a minimum, but this minimum is not lower than this, so we ignore it, we throw it away. We keep moving. At this point, we realize that we have already gone up by beta since this minimum. If we do that, then we can say that this minimum is persistent. We can add this to the set of persistent points and move on. Okay? So that is how the online algorithm works. So in particular, you just need to maintain a buffer of 4 points. Let's say this part is the integer. This part has already been processed. We know exactly all minima and persistent maxima and minima here. We still keep a pointer here. And now we have this minimum that we are trying to decide if it is persistent or not. We keep a pointer here, and we go on moving until we are somewhere high so that we can check that beta threshold and say that this is the minimum. Then we put this in that category and move to the next part. And you can show that you just need to keep a buffer of 4 points and check every time a new point comes in. This means that the cost is O of 1 per input point. Okay? Each incoming point is processed in constant time. So we can do real-time simplification with this, which is awesome, except that our goal is to get rid of noise, and noise itself can have sharp turns. Okay? In fact, noise tends to have very sharp turns. So in this case, all these things have high curvature. They are sharp turns. But the observation is that if we take a point like this, instead of taking its immediate neighbors to compute the angle of turn, if we take something farther away, like this point and this point, that are distance at least this on the boundary of this circle or farther, then this angle from here to here and here to here is relatively small. It's just going like this, just small turn to go there. Okay? So that is the idea, that take neighborhoods of different resolutions around the points of different scales to get rid of noise that produces sharp turns. If you do that, for example, in this trajectory, so the trajectory itself is in black. It goes like this. Okay? If we take a medium scale simplification, let's say scale 5, then we will get something like this. At a very high scale, like scale 9, we get this. So very high scales are probably not very good because it induces high errors, but a medium scale is likely to be good. Also, this depends on what your application is. Okay? Okay. So, but we would like to compute all these simplifications at the same time. Okay? Because we don't know how someone wants to use this data. We want to compute them all at the same time so that whatever the application wants, it can pick data of corresponding resolution. Okay. So the good thing is that this also can be done online at a cost of O of 1 per thing. So the algorithm works like this, that for scales j to log of the length of the trajectory, take a scale that is 2 to the j. So we are taking exponentially growing scales. Compute the persistence. Then filter surviving points to scale 2s, meaning that the points that survived persistence, you again throw away from them points if they are successive points within distance 2s. We don't want successive points to be very close. If there are, we just throw one away. Okay? We keep on doing that. In the end, these are the points that have survived persistence, and they are 2s apart from each other. Then you go to the next scale. So when you're going to the next scale, you have already thrown away points that did not survive persistence and points that are less than 2s apart. Now at the next scale, you again do persistence, and you throw away points again. Okay? So repeat that for log of the length of the path. So that produces multi-resolution simplification. It tells us the important points at different scales. So it is like this, that we start with all points. Some of the points survive to scale 1, like this. Now we execute persistence and the 2s sampling on this set of points, which leaves a smaller set of points surviving like this. Okay? We repeat the same procedure and get an even smaller set. So out of these, the things that last to the highest levels are the most important points. And the ones that are at the next level are the next most important points. So this kind of gives a ranking of your importance of points. Okay? So in this case, these three are this, this, and this. The next one is this. The next one, this is probably this. I'm not sure. Yeah, this, etc. Okay? So it produces essentially a very intuitive result. Okay. And this can be done online. We are going to do the persistence-based simplification simultaneously for all the levels. Okay? Except that at the lowest level, we add the new incoming point. Whichever is the new persistent point added at the lowest level, we promote it to the next level. Consider it as an addition. Do that. Promote the next point to the higher level, etc. Okay. And this is a multi-resolution simplification at O of 1 per point. The reason is that in expectation, each point survives only to a constant level. There are log n levels in your tree. You can check that each point can rise only to a constant level if you're going to have log n levels at all. Okay? This means that this promotion thing cannot go on for too long for any point. Okay? Okay. Very good. So here are some more examples. This is from the GeoLife data set that it's an actual trajectory. In this case, I mean, the simplifications pretty much overlap the trajectory because it's very nicely right angle turns. So we drew some trajectories by hand, arbitrary shapes, etc., and it gives quite intuitive results. It removes all this noise very nicely, etc. Okay? And we compared in experiments with some other methods. So this is a very old method which says that you are trying to compute an approximation that stays within an epsilon distance of the original trajectory, which is that you take the complete graph, you take edges between every pair of points, then you consider this narrow tube around the original trajectory, and you throw away any edge that is not completely inside that tube. Okay? This gives you a much smaller set of edges, and the shortest path from source to destination in this smaller set of edges is your approximation. You can show that for epsilon approximation, this gives optimal result, that is, result with fewest number of vertices. But it requires an n-squared computation because your complete graph has n-squared edges. That itself makes it very inefficient. So in fact, on the GeoLife data set, it was very difficult to apply this. We had to play some tricks to do some heuristics to make it simpler. There's the Douglas-Pucker algorithm, which is another very famous one, which is not optimal but much more efficient in practice, which says that start with the line from the source to destination as your approximation. Then at the point that is farthest from this approximation, insert that point. So now instead of this, you have this as your approximation. Now at the point that is farthest from your current approximation, and keep doing that. This is also n-squared, but in practice, this gives much better results than the EDMA. Okay. So we did the experiments. And we plot here the maximum error, the average error, and the median error everywhere against the size of the approximation, the fraction of the number of points of the total number of points that were there. So EDMA gives very good results in all cases, which is not surprising. Even with like 10% points or something, it has low errors. Douglas-Pucker also gives very good results. The good thing is that our algorithm gives only slightly worse results, but in an online manner. So none of those other algorithms you can do online. But if you do our algorithm, it works online, gives slightly worse results, but still very good. So for example, if we take the median error, if you use only like 5% of your points, the median error is dropping to about 5-6 meters. Which is fine in practice because your GPS localization likely has 5-6 meters of error anyway. Okay? So we also did experiments on cell signal, light signal, and you basically get similar results. The only other observation is that here you can apply fast Fourier transforms on these signals to simplify, and fast Fourier transform does not give you very good results because it misses all these sharp features of the data. Okay? Another thing is to detect hotspots. So the idea was that the traffic hotspots, or your major crossings and such things, are places where a lot of people take important turns, the large turns. Okay? So if you do that, then in the crowded areas of the trajectories, you get lots of these important turns. So here the squares kind of represent the important turns. And if you do that, you get lots of crowded turns around the important areas. Okay? So this particular thing needs some more study, but I believe this is a good heuristic to detect hotspots. So in summary, we talked about online learning and simplification. In a sense, this online learning and online simplification are kind of the same thing. So learning is basically simplifying your data. Learning is filtering out the essential pattern from your raw data set, right? But the important thing is that it has to be fast, simple, and real time, which we find that in a lot of cases we can do. It remains to be seen where else we can do it. And we need adaptive methods in smart systems, things that can adapt to new environment, new users, new devices. Yeah, by the way, for the indoor-outdoor detection thing, we also tried it on different devices. So you do the initial learning on one device and try the detection and learning on the other device. We found that it works reasonably well, but not perfect. Possibly some more analysis of how you can do device calibration quickly might help there. And context is useful in adapting your phones and services. So it is kind of useful if you can have your adaptive methods of context detection. And simplification is, in general, useful in data analytics. We are now looking to do better analysis of trajectories using these simplifications. So that's all. Thank you.